Welcome back to part 2 of Module 7, Lesson 3, where we are working with equations that have variables on both sides. Now, we left off in example 2, and I think this is the first time I've stopped in the middle of an example because this next step, it's a little bit intense, and I wanted you to be fresh before we looked at it. This one they refer to as solving the equation using the least common denominator to eliminate fractions. I always learned this is rationalizing the denominator, and they're going to do things that are a little different than I would do, but it still works. So they started off with the same problem we had in step 2 or slide 2 of this problem, only this time, and this time they're starting it the same way where they're finding that common denominator of their x terms. From there, they decided that they're going to take and get rid of the fractions. To get rid of the fractions, they're multiplying both sides by their denominators. The denominator was 6, so they multiply the left by 6, and they multiply the right by 6. In doing that, the 6 times 4, 6x, well, that just became 4. And the 6 times negative 1, that became negative 6. On the right-hand side, 6 times 9, that became 54. And 6 times 1, 6x, that just became 6 6x's, also known as 1x, also known as x. Now your fractions are gone, and that means this problem is going to be a lot easier to work from here on out. So when we go from there, we're going to take and subtract x on both sides. This way, once again, we're keeping our x terms positive, and that's going to leave me with 4 plus 1, which is going to give me 5x, minus the 6 is left with the 54. Next, we're going to undo addition and subtraction by adding 6 to both sides right here. These 6's are going to zero each other out, which is going to leave you with 5x is equal to 54 plus 6. That's going to give me 60. And now we're going to isolate the variable by dividing 5 on both sides. You can see it here finally. And then the 5 divided by 5 is 1. 1 times x is x. And 60 divided by 5, well, that's going to be a happy little 12 right there. And this right here, whoop, is all the supporting work they did for that one. Now I'm going to take one more example with this problem, and I'm going to rationalize the denominator a different way, but it's going to give us the same answer. After thinking about it for a moment, I realized that the other way I was going to show you, it wouldn't work. It would have given us the wrong answer. So we're going to skip that and instead let you guys pause the video and work extra example 2 on your own. Now you can use either approach you want. You can work it the painstaking long way, or you can rationalize those denominators and work with just whole numbers in the end. Your choice. How'd it work out for you? Oh, let me show you what I'm going to do. First thing I'm going to do is rationalize the denominators, but to rationalize the denominators, the first thing I really have to do is find the least common denominator of every denominator that's in there. And the textbook, when they did it, they didn't really show the fact that they had 1's there as well. So we need the least common multiple of 2, 1, 4, and 1, and that least common multiple, it's going to end up being 4. So I'm going to take this, in fact, I'm not even going to bother changing this. I'm going to leave that alone just like it is. No reason for me to manipulate that into 2 fourths. I'm just going to worry about the fact that I know the least common multiple of 2, 1, 4, and 1, that's going to be 4. So I'm going to go from there, and I'm going to say 4 times the original problem, 1/2 p plus 7, is equal to 4 times the other original problem, 3/4 p plus 9. Now I'm going to take my 4's, I'm going to distribute them through the grouping symbols. So I'm going to have 4 times 1/2 p plus 4 times 7 is equal to, and on the right hand side, 4 times 3/4 p plus 4 times 9. I got an improper fraction here and an improper fraction here. That's going to allow me to simplify. Now 2 goes into 2 once, 2 goes into 4 2 times. And then on this side, 4 goes into 4 once, 4 goes into 4 once. Now I can multiply. 2 times 1 is 2, 1 times 1 is 1. That gives me 2 over 1, also known as just 2p. Plus 4 times 7, That's going to give me 28 is equal to, now 1 times 3 is 3, 1 times 1 is 1, 3 over 1 is 3p, plus 4 times 9, that's going to give me 36. Now I'm going to move my variable numbers to one side. I want to keep them positive, so that means I've got to move them to the right by subtracting 2p on both sides. That's going to zero out, leaving 28 is equal to 3p minus 2p is just 1p plus 36. From here, I'm going to take and subtract 36 from both sides, undoing addition and subtraction, minus 36 again. Those zero out, and it's going to leave p is equal to 28 minus 36. Signs are different. Find the difference, which is going to be 8, with a sign in front of your larger number going in front of your answer. So negative 8 should be my correct answer. Take it, plug it in here, and check, and my answer checks. Now once again, whoops, clear that little mark out. This is what would showing your work would look like on that problem. That's what I would have to see on a problem like that in your homework. Now this leads us to our next inquiry question, which asks, why is writing an equation a useful way to represent and solve a real-world problem? Well, it just makes things simple, folks. Let's dig into it and find out more. The cost per person to bowl at a bowling alley is $5.95 per game, and it includes your bowling shoe rentals. Bowling alley B charges $4.45 per game, but they want $3 for a bowling shoe rental. Drag the expressions to the appropriate bins to describe each situation. The variable G represents the number of games. Well, bowling alley A was just a flat $5.90 per game. So that's going to be bowling alley A. So I'm going to drag that one and drop it here. Meanwhile, bowling alley B wanted to do $4.45 plus $3 per game for bowling shoes. That's going to be bowling alley B right there. Now, if we wanted to find out when you would break even going to the two bowling alleys, then we'd have to just set equal signs to those and then work on isolating the variable. Or you could go all painstakingly and then create a table where you'd have 595 times 1 is 5.95. Meanwhile, if we did one game here, it would be 445 plus 3, which would be $7.45. If we did that times 2, that would become $11. Let's go ahead and start cheating here because I don't want to waste a whole bunch of time. Stand by. Whew, I'm tired after that. But you can see that you could take and where in the beginning bowling alley A was a better price per game. The further down you got, you finally reach a crossing point here at 5 games where it was cheaper to go to bowling alley B. That's because bowling alley A included the cost of your shoe rental on every game. Bowling alley B, they didn't care how many games you played, you only had to pay for your shoes to rent one time. As far as the question of which bowling alley would you want to go to, well, it depends on how many games you want to play. I'm usually good for 2, maybe 3 games. 5 games? No, I'm not doing that. Now the question says, how could you use the two expressions to write an equation that could be used to determine when the cost to bowl at the two bowling alleys is going to be the same? So what we're going to do is we're going to take those two expressions and we're going to set them equal to each other. And you can see they did that right here. $5.95 times G, that's bowling alley A, is equal to bowling alley B's $4.45 times G plus the $3. So why is writing an equation a useful way to solve a real-world problem? Well, I'll tell you why. It allows you to save money. Easy way to take and figure out which bowling alley would be the better deal for you. This is where I'm going to finish part 2 of this video, and when we come back for part 3, we're actually going to be converting some of these word problems into equations with variables on both sides.